Hi everyone, this lesson is carrying on with horizontal circular motion, and in this lesson we are looking at two things. So one of them is the conical pendulum. So you're all familiar with the pendulum, which is any mass at the end of a string, and a pendulum usually just goes back and forth. So what is a conical pendulum? So a conical pendulum, instead of going back and forth, actually goes around in a circle. So when it goes around in a circle, the string actually describes a cone, and that is why it's called a conical pendulum, and the circle is a horizontal circle. So let's just analyze this motion, okay? And I'll tell you why we're learning about this, because it leads us quite nicely onto banked curves. So a conical pendulum is this one going around in a circle. So you have, if you just look at the mass at any particular point, there are two forces, just two forces acting on it. And the two forces are the force of gravity, which is equal to mg, and there is your tension force. These are the only two forces. Now, if we resolve the tension force into two components, so this is your mass, and we have gravity that is acting vertically downwards, which is my mg, and I'm just going to draw my tension force as a dot for now, and I'm going to resolve this tension force into two, its vertical component and the horizontal component. Okay, now this is your theta. Okay, so this theta is the same as that, and that's my ft. So this becomes ft cos theta, and the horizontal component becomes ft sine theta. Now, because the pendulum is going horizontally, we say that it's in vertical equilibrium. That means the forces in the vertical direction are balanced. So what are the forces in the vertical direction? So the vertical forces are mg, which is my gravity force, and the vertical component of the tension force. So we say that mg equals ft cos theta. So if we want to find ft, we get ft is mg divided by cos theta. And so the only unbalanced force is ft sine theta. So this is one of them. So my ft sine theta becomes equal to my centripetal force. Okay, so my centripetal force is provided by the horizontal component of my tension force. Now, if I just go another step further, we learnt that centripetal force is actually mv squared over r. So if you're asked to find the speed of this thing going around a circle, there are a couple of steps, and I'll show you a short method after this. So my v squared is ft sine theta times r divided by m, and then you find what is ft sine theta. You get a number, and that's how you get v squared, and then if you square root, you can find the value for v. So that's our conical pendulum. Now this leads quite nicely on to banked curves, which is the next part of this video. So what are banked curves, and why is that important? Okay, this has to do with cars going around circles. So I'm just going to go back a step to look at what happens if you have a horizontal flat road and there's something going around in a circle, and we learnt that the forces acting are your gravity force mg, which acts vertically down, and then you have your, at right angles to the road or the surface of the road, you have your reaction force, and these two cancel each other because the car is in vertical equilibrium. And the only unbalanced force that provides centripetal force is your friction force. Now the thing is, you can't always rely on friction to provide centripetal force, because if the tires of your car, the tread is worn out, if they're bald, there's not going to be enough friction between your tires and the road to provide centripetal force. You could also have conditions like wet roads, icy roads, oil on the road, something spilt on the road. So it's not always possible to rely on friction to provide centripetal force. So to overcome this and to be able to do higher speeds, what people have done is they instead of having a horizontal road, the road is at an incline, so it is banked, so that the outer edge of the curve is raised compared to the inner edge. It's kind of like the velodrome for cycling. Okay, so this is how you draw a banked curve. So the outside edge is raised. This is your circular road, and this is something going in a circle. Okay, so let's say that's the object. Let's try and do all the forces acting. So you always have gravity force that acts vertically down. So that's my vertical to the horizontal. And then at right angles to the surface of the road, now the surface of the road is no longer horizontal, you have your reaction force. Okay, now because the car is in vertical equilibrium, it's not going up or down, vertically up or vertically down, it's going in a horizontal circle. The vertical forces are balanced. So what are the vertical forces that are balanced? It is gravity force, and it is also the vertical component of your reaction force, which is Fr cos theta. Where's my theta? That's my theta. Okay, and so what have I done? I have resolved the reaction force into its vertical component, which balances the gravity force, and then into the horizontal component, which is Fr sine theta, which provides centripetal force. So let's look at all this together. My centripetal force, which is mv squared over r, is provided by the horizontal component of my reaction force. My gravity force, Fg, which is mg, is provided by the vertical component of my reaction force, which is Fr cos theta. Now I'll just show you an easy way to solve problems. Okay, this is just some fun with numbers and fun with maths. What happens if you divide one thing by the other? So if you look at this, I can take the Fr out, divide both sides by Fr, and m is also a common factor. So what do I have left? I've got v squared over rg equals, if you divide sine theta by cos theta, you get tan theta. So this is quite a useful relationship to know, and I can also rewrite this as v squared equals rg tan theta, or v is equal to square root of rg tan theta. So this is quite a useful formula for solving problems on banked curves. Now why are banked curves useful is because your centripetal force is no longer only dependent on friction. So for this one I have avoided, I haven't taken friction into account. So if you did have friction, it would be acting along the surface of the slope towards the center. Okay, because friction is always along the surface. Your centripetal force is the horizontal component of the reaction force. So what actually happens is, as you increase the angle of banking, your horizontal component gets bigger and bigger. So you're going to have a bigger centripetal force as you increase the angle of banking. So how does that help? The radius has stayed the same. The mass of whatever it is that's going around in the circle has stayed the same. But if your Fc increases, your radius and mass stays the same, you can do greater speeds. So you can do greater safe speeds when your surface of the road is banked. Bye for now.